So this was from Algebra group theory homework. On page 13, number 1, we have the group G of congruence classes modulo 15. And H be the subgroup generated by the congruence class 3 plus 15Z. So that means H consists of all multiples of 3 plus 15Z. So we have 3 plus 15Z. If we add it to itself, we get 6 plus 15Z. If we add it to itself, we get 9 plus 15Z, 12 plus 15Z, and then 15 plus 15Z, which is the same as 15Z. That is, this in general, in a group, in an additive group, the subgroup generated by some element X is the set of all multiples of X. And so in this case, X is 3 plus 15Z. So if you take NX, that's N times 3 plus 15Z. That's 3N plus 15Z. As N goes from 0, plus, minus 1, and so forth. But these congruence classes, the multiples of 3, you have 0, 3 plus 15Z, 9, 12, 9 plus 15Z, 12 plus 15Z, and 5 times 3 is 15, which is the same as 0 mod 15. So the subgroup H is this group consisting of 5 congruence classes, right? So that's what H is. Right? So you can't start the problem, parts A or B, until you know what H is. And then we have to look at the quotient group, the left cosets. So G is Z mod 15Z. H is the subgroup generated by 3 plus 15Z. So what are the cosets? G mod H. So you have H (1 plus 15Z plus H), 2 plus 15Z plus H. What does this mean? 1 plus 15Z plus H, you just add 1 to all the elements of H. So mod H, so this is 1 plus, I'll just write 0, 3, 6, 9, and 12. Mod H, this is mod 15. This is just my sloppy writing, but this is 1 plus 15Z, 4 plus 15Z, 7 plus 15Z, 10 plus 15Z, and 13 plus 15Z. This is one coset. And second coset is you take 1 plus 15Z plus H. So you're adding 2 to each of the elements in H. So you get 2 plus 15Z, 5 plus 15Z, 8 plus 15Z, 11 plus 15Z, 14 plus 15Z. This is the second coset. And of course, 0 plus H is just H. That's 15Z, 3 plus 15Z, 6 plus 15Z, 9 plus 15Z, 12 plus 15Z. So we have 3 cosets. These are the left cosets. And the right cosets are the same as the left cosets because this is an abelian group. And the index of G and H is the number of cosets, which is 3, which is also the order of G over the order of H. The group G has 15 elements. The subgroup H has 5 elements, and 15 over 5 is 3.
Thank you, Professor.
Okay. Other questions? So we start a new chapter today. We have been talking about groups, and today we're going to talk about rings. So to have a picture of what a ring is, just think of the integers z, the ordinary integers. 0, plus minus 1, plus minus 2, plus minus 3, and so forth. This is the ordinary integers. This is an additive abelian group. You can add integers, but we can also multiply. Integers. So in the set of integers, there are 2 operations, addition and multiplication. And a ring is going to be a set where you can both add and multiply. So this is the first example. This will be the first example of a ring. So in a ring, this is going to be an additive abelian group with also a way to multiply things with the multiplication. So you have addition and multiplication. All right. What's another example? So suppose we look at, say, r square brackets x. This is all polynomials in the x. So if you have a polynomial f of x equals 7x squared plus 2x plus 3, and g of x equal to 5x cubed minus x squared plus 11, you can add them. And you get whatever you get, 5x cubed plus 6x squared plus 2x plus 14. There's addition of polynomials. But you can also, so this is an additive abelian group, adding and subtracting polynomials. But you can also multiply. Polynomials. So when you're looking at polynomials, you not only have addition, you have multiplication. All right. Let's look at, so this is a second example. First, second, third example. Suppose we look at M2 of R. This just means all 2 by 2 matrices with coefficients that are real numbers. And if you have 2 matrices, you can add them. You just add coordinates. All right, so this is addition of matrices. And adding matrices is another example of an additive abelian group, but we can also multiply matrices. Can also multiply 2 by 2 matrices. All right. You know how to multiply A, B, C, D, E, F, G, H. So the set of 2 by 2 matrices will be a third example of what we are going to call a ring. Okay. So, but the main idea is that in a group, you have just one operation, addition or multiplication. If it's an abelian group, we often write the operation as addition. But if you also have a way to multiply elements, then you might have something called a ring. So I have to give a definition of a ring, but having some examples in mind makes the definition a lot clearer. And as I go through the definition of ring, you should keep in mind, for example, the integers, and see that everything I write down is true for the integers. So a ring R with 2 binary operations of addition and multiplication So a ring R is a set with binary operations of addition and multiplication that satisfy the following properties. First, R is an, under addition, it's an additive abelian group. So that says everything you need to know about addition. What about multiplication? Well, multiplication is associative. That means xy times z is x times yz for all x, y, z in the ring. And thirdly, we have distributive laws. That x times y plus z is xy plus xz, and x plus y times z is xz plus yz. All right. So again, this is just distribution, which you can do with the integers, for example. There's also a multiplicative identity. Let's just call it 1, such that x times 1 and 1 times x is always equal to x for all x in the ring. And that's it. So if you have an additive abelian group in which there's also an operation of multiplication of elements that's associative, where multiplication distributes over addition and there's an identity, then it's called a ring. And there's a fifth property that doesn't always have to be satisfied. If multiplication is commutative, if xy equals yx for all x and y in R, then R is called a commutative ring. Okay. So for example, the integers under addition and multiplication is a commutative ring. Right? 2 times 3 equals 3 times 2. And the polynomial ring is also commutative. But the matrix ring, say 2 by 2 matrices, is not commutative. Because when you multiply matrices, the order matters. Any questions about this? So this is a new definition. This is our new topic in algebra. So let's prove some beginning theorems. Actually, they're just lemmas, they're simple things about rings. So suppose R is a ring with, as a group, it's an additive abelian group. So let's write the additive identity 0, and let's write the multiplicative identity 1. So the following is obvious if you're thinking about numbers, but it's not obvious for a ring. If you take any element for all x in the ring, if you multiply x by 0 on the left, you get 0. And if you multiply x by 0 on the right, in both cases, you get 0. Right? And also, if you multiply x by -1, or x on the other side by -1, that's minus x. And for all x and y in the ring, minus x times minus y is xy, and minus x times y, or x times minus y, is minus xy. So you tend to think of these things as obviously true, but they're not obviously true. They're only obviously true for the numbers that you grew up with. But for an abstract ring, it's not so obvious that this is the case. Right? So each of these things has to be proven. So first of all, proof. So this ring R is an additive abelian group. So this means that for every element x in the ring, there is an element minus x, this is one element, such that x plus minus x and minus x plus x is 0. Okay. So we know that 0 is the additive identity. So 0 is 0 plus 0. Right? So 0 times x is 0 plus 0 times x. And by the distributive law, this is 0x plus 0x. Now, I don't know what 0x is, but it does have a negative. So add minus 0x to both sides of this equation. So you get 0x plus minus 0x is 0x plus 0x plus minus 0x, which I can, by associativity, I can think of as like this. Now 0x plus its negative is 0. And this is then 0x plus 0. And 0 is the identity for addition. So this is 0x. So I just proved that if you multiply any element by the 0, you get the 0 element. And if I take this same equation and multiply on the right by x, x times 0 is always equal to 0. So that proves this first statement. Okay. Any questions about this? So we're starting to prove things about rings. We're doing ring theory. Now, we also know that 1 plus minus 1 is 0. So 0, which is 0 times x, because I just proved that 0 times any element is 0. But I can write 0 as 1 plus minus 1 times x, which is 1 times x plus minus 1 times x. 1 times x is x, and this is whatever minus 1 times x is. So if I add minus x to both sides, minus x is minus x plus 0 is minus x plus minus 1 times x. But this is 0. This is 0 plus minus 1 times x. So I get minus x is minus 1 times x. That is, if I multiply any element in the ring by minus 1, I get the additive inverse of x. I get minus x. Okay. And for the other parts of the proof, they're all written down in the notes, and one has to go through them very, very, very carefully, maybe several times, to try to follow the reasoning. Okay. So suppose we have a ring R, an element X in the ring is called a unit. So under multiplication, the ring is not a group. You can multiply elements, multiplication is associative. There's an identity, but elements don't have inverses necessarily. For example, in the ring of integers, 2 has no inverse. We say X in R is a unit if there exists a Y in R such that X times Y and Y times X equals 1. So an element in a ring is a unit if it has a sort of a multiplicative inverse. So in the ring Z, for example, 2 is not a unit. What would the inverse of 2 be under multiplication? It would be a half. But a half is not an integer. So in the ring Z, 2 is not a unit. Right? 1 is a unit and minus 1 is a unit. And they're actually the only units. But in any ring R, there may or may not be units. Well, of course, 1 is always a unit, because 1 times 1 is 1. So if you take X equal 1, Y equal 1 works. And this sort of Y, if it exists, is unique. So that Y and Z in the ring R satisfy the equations XY equal YX equals 1 and XZ equal YZ equals ZY equals 1. So I claim that Y equals Z, an element only if it has an inverse, its inverse is unique. So I can say Y is Y times 1. 1 I can write as xz. By associativity, this is yx times z, but yx is 1, so this is 1 times z, this is z. So y equals z. So if an element is a unit, and that means there's a y such that xy equals y, x equals 1, and there's only one such y. So if xy equal y, x equals 1 in the ring R, then y is called the inverse of x. And it's because it's unique, we can denote it as x to the minus 1. So x to the minus 1, it doesn't mean 1 over x. It means an element in the ring such that x times that element is 1. And some elements have inverses and some don't. Some elements are units and some aren't. So we have another lemma which says the following. In the ring R, the set of units of R is a multiplicative group. And which we denote as R, that time sign as a superscript. And the proof, well, first of all, 1 times 1 equals 1. So 1 is a unit. So 1 is in this set, R star, R times R star. So I want to show this is a group. So I need to show it's closed under multiplication and it has inverses. We know multiplication is associative to begin with. So if x and y are in the set of units of the ring R, what happens if I multiply xy by the element y inverse x inverse? If x and y are units, they have inverses, so I can multiply them. So this is the same as x, y inverse, x inverse. Y inverse is 1. So this is x times x inverse, which is 1. And similarly, y inverse x inverse times xy is 1. So xy is a unit. If x and y are units, so is their product. And of course, just from the equation x inverse equals x inverse x equals 1, that implies that x inverse is a unit, if x is a unit. So associated to every ring, we have the group of units. Let's look at some examples. What about if we take R equal to the integers? So Z star, the only units are 1 and -1, right? Because 1 times 1 is 1, -1 times -1 is 1. So 1 and -1 are units.
Yeah.
Right?
What?
Right? 1 and -1 are units. 0. 0 times x is 0. It's not equal to 1. So 0 is not a unit. Never. What about number n? If n is different from 0 plus or minus 1, then nx equal 1 has no solution x and z, like 3x equal 1. There's no integer such that 3 times that integer is 1. So n is not a unit. So the group of units in the integers are just the two numbers, 1 and -1. And that's a multiplicative group. Right. What about in the group M2 of R? This is all 2 by 2 matrices. What are the units? Well, so A, B, C, D inverse exists if and only if the determinant AD minus BC is not equal to 0. So if X is the matrix ABCD, then X inverse is, if AD minus BC is different from 0, let me just call that delta, so I don't have to keep writing it down. This is going to be D over delta minus B over delta minus C over delta, A over delta. And you can check that if you multiply these two matrices, you get the identity. In this ring, the multiplicative inverse, sorry, the multiplicative identity is the 2 by 2 identity matrix, 1, 0, 0, 1, just as the 0 matrix for addition is 0, 0, 0, 0. So in M2 of R, the group of units is all 2 by 2 matrices where AD minus BC is not 0. This is a multiplicative group. It's not a billion, but it is a multiplicative group. Right. Let's look at another example. Suppose for my ring R, I take the real numbers. Right? So you have addition and multiplication. What is the group of units? It's every real number except 0, because if x is not equal to 0, 1 over x is a real number, and x times 1 over x and 1 over x times x equals 1. So every non-zero element is a real number. And similarly, if we take R to be Q, the rational numbers, the fractions, or R equal to C, the complex numbers. So the rationals, the reals, the complexes, these are commutative rings. Such that every x not equal to 0 is a unit. And a field is a commutative ring such that every non-zero element is a unit. So the rational numbers, the real numbers, the complex numbers, these are all examples of rings. Sorry, all examples of fields. What's another example of a field? Well, suppose P is prime. If you look at the congruence classes Z mod PZ, this is a field. Every non-zero congruence class has an inverse. And why is that? Well, if A is not congruent to 0 mod P, then the congruence AX congruent to B mod P has a solution for all B. So AX congruent to 1 mod P has a solution. So there exists an integer X such that AX is congruent to 1 mod P. This says exactly that the congruence class A plus PZ times the congruence class X plus PZ. This is the congruence class of AX plus PZ. And if AX is congruent to 1, this is 1 plus PZ. So this congruence class has an inverse. A plus BZ is a unit if A is not 0 mod P, or A plus PZ is not the congruence class PZ. So X plus PZ is a field. Every congruence class has an inverse. So this is actually very interesting because this is a finite set. There are only P elements in it, and P minus 1 elements are units. What about Z mod MZ for composite M? So suppose M is composite, and let R be Z mod MZ. So we already saw when we were studying congruences that the set of congruence classes modulo M satisfies all the properties of a ring. It's a ring, right? I mean, addition of congruence classes, we know very well. And multiplication of congruence classes. We know very well. So suppose we want to compute the group of units in Z mod MZ. So we know that if A and M are relatively prime, then AX congruent to 1 mod M has a solution. And so A plus MZ times X plus MZ which is AX plus MZ. And if AX is congruent to 1 mod M, this is 1 plus MZ. So A plus MZ is a unit. So A plus MZ is an element in the group of units of this ring. Let's look at an example. Suppose I just take M equal to 4. So I'm looking at the congruence classes mod 4. So that's 4Z, 1 plus 4Z, 2 plus 4Z, 3 plus 4Z. So A and 4 are relatively prime if A equals 1 or A equals 3. And 1 plus 4Z times 1 plus 4Z is 1 times 1 is 1 plus 4Z. And 3 plus 4Z times 3 plus 4Z is 3 times 3 plus 4Z, which is 9 plus 4Z, and 9 is congruent to 1 mod 4. So 1 plus 4Z and 3 plus 4Z are units in this ring. They have multiplicative inverses. If I take 0 plus 4Z times any x plus 4Z, that's 0 times x plus 4Z, which is 0 plus 4Z. It's definitely not 1 plus 4Z, no matter what x I pick. So 0 is not a unit. What about 2 plus 4Z? If I multiply that by any x plus 4Z, that's 2x plus 4Z. And an even number is never congruent to 1 mod 4. So 0 and 2, the congruence classes of 0 and 2 are not units mod 4. So the group of units is exactly these two congruence classes. So the number of elements in this group is 2, which is exactly phi of 2, where phi is the Euler phi function. Any questions about this? Let's see. Let's look at another example. Suppose I take M equals 6, and I want to find the group of units mod 6. So this is all congruence classes A plus 6Z, such that A plus 6Z times X plus 6Z equals 1 plus 6Z, such that there exists a class X plus 6Z such that this product is 1. So this is all A plus 6Z such that AX is congruent to 1 mod 6 as a solution. And this is all A plus 6Z such that the common divisor of A and greatest common divisor of A and 6 divides 1, which means the greatest common divisor of A and 6 is equal to 1. What numbers between 0 and 5, or between 1 and 6, are relatively prime to 6? Just 1 and 5. This is 1 plus 6z and 5 plus 6z. So again, if I take the ring of congruence classes mod 6, the group of units has 2 elements, and the Euler phi function phi of 6 is equal to 2. So in general, let's try to compute the group of units in the ring of congruence classes mod M. So A plus MZ is a unit in this ring if and only if there exists X plus MZ such that A plus MZ times X plus MZ, which is AX plus MZ, is equal to 1 plus MZ. And this is possible if and only if AX congruent to 1 mod M has a solution. If and only if this congruence has a solution. And this is true if and only if 1 is congruent to 0 modulo the greatest common divisor of A and M, which just means that A and M are relatively prime. So the group of units Z mod MZ is the set of all congruence classes A plus MZ, where A is an integer between 0 and M minus 1, and A and M are relatively prime. So in particular, the cardinality, the size of this set, is the number of integers from 0 to M minus 1, relatively prime to M. That's phi of M, which is our beloved Euler phi function. Okay. Any other questions? Any questions? Let's look at another example of a commutative ring. So this is a commutative ring from calculus. Let's write C01 is the set of all functions f on the interval 0 to 1, real valued functions such that f is continuous. So y equal f of x, some continuous function, That's an element of this set. And if f and g are continuous, then f plus g and minus f are continuous, and f times g is continuous. That is, the sum and the product of continuous functions are continuous. So this set is closed under addition and multiplication. And under addition, it's an abelian group. What is the additive identity? It's just the function f of x equals 0 for all x. Because if you add this function to any other function g, you just get back g. What is the multiplicative identity? It's the constant function f of x equals 1 for all x. Because if you multiply 1 times any function, you just get back the same function. What does it mean to say that a function in this ring is a unit? So f of x is a unit if there exists g of x, also a continuous function, such that f of x times g of x is the identity function is 1, which means certainly that f of x is different from 0 for all x. So if you have a unit, that function is never 0. Of course, it also means that the function is always positive or always negative. Because if you had some value a where the function was negative and a value b where the function was positive, they teach you in calculus that if a continuous function is negative at a and positive at b, it has to cross the x-axis somewhere, so it's 0 somewhere, and then it wouldn't be a unit. But if f of x is different from 0 for all x, then the reciprocal function 1 over f of x is continuous. So the group of units of continuous functions from 0 to 1, it's all f from 0 to 1, such that f of x is different from 0 for all x. So in this ring, the units are the continuous functions that are always either always positive or always negative. No. In the ring z mod 6z, 2 plus 6z is not 0. And 3 plus 6z is not 0. But if I multiply these two non-zero elements, 2 plus 6z times 3 plus 6z, that's 6 plus 6z, that's 0 plus 6z. So the product of two non-zero elements is 0. That's a kind of a messy situation, and you don't find this in the integers. In z, a product of two numbers is 0 if and only if a equals 0 or b equals 0. So the integers are a much nicer ring in some sense than the integers mod 6. We define an integral domain is a commutative ring. Addition is always commutative. Commutative ring means multiplication is commutative. This is a commutative ring such that x different from 0 and y different from 0 implies xy is different from 0. So if a ring has this property, it's called an integral domain. Another way of saying that is to use the expression a zero divisor. A zero divisor in R is an element X in R such that X is different from 0 and there exists a Y in R, Y different from 0, such that XY equals 0. So in an integral domain, or let's say an integral domain, another way of defining this is a commutative ring that has no zero divisor. So the prime example of a commutative ring is the integers. Sorry, the prime example of an integral domain is the ring of integers. Polynomials also give another example. So this polynomial ring with coefficients in the field of real numbers is also an integral domain. One way to say this is the following. So the degree of a non-zero polynomial is the highest power of a non-zero polynomial, let's say f of x, is the highest power of x in f of x with a non-zero coefficient. So if we have 3x squared minus 2x plus 5, the degree, the highest power of x is x squared, so the degree is 2. We have the degree of minus 7x cubed plus 100,000 x squared minus 19. The highest power of x that occurs is 3. If I have the degree of 0 times x third plus 5 times x plus 1, I have an x cubed, but with a coefficient of 0. It's like it's not there. The highest power of x with a non-zero coefficient is x to the first power. So this polynomial has degree x. And if we take two polynomials, let's say a has degree m,
sorry, Professor, can I interrupt for half a second? So the two above, the degree of negative 7x squared plus 10,000x squared minus 14 cubed is 3?
Yeah.
Okay. And so
the highest power of x is x.
got it. Okay, perfect. Thank you.
Here, the highest power of x is x cubed, but the coefficient is 0. So that doesn't count. The highest power of x with a non-zero coefficient is x, or x to the first power. So this is degree 1. So if I take a polynomial of degree m, so am is not 0, and I multiply it by a polynomial of degree n, bn x to the n, so bn is also non-zero. When I multiply these, I get am bn x to the m plus n plus lower order terms. And this is a field. If am and bn are non-zero, am times bn is non-zero. So let me call this f of x and g of x. So the degree of the product f of x times g of x is m plus n, but m is the degree of f of x and n is the degree of g of x. The 0 polynomial doesn't have a degree. A non-zero constant polynomial has degree 1. Right? I mean, if you had the degree of the constant polynomial 7, 7 means 7 times x to the 0. So the highest power of x with a non-zero coefficient is the 0th power. And in general, the degree of c is 0 for constant c different from 0. And the degree of the 0 polynomial is undefined. Right? So the constant 0 has, as a polynomial, has no degree. A non-zero constant has degree 0. And if the degree of f times g is the degree of f plus the degree of g, this means fg is not 0 because it has a degree. So the product of two non-zero polynomials is non-zero. So this ring of polynomials with coefficient in x is also an integral domain. Again, this is what you know from high school, and this is just putting this in the context of abstract algebra. The product of two non-zero polynomials is non-zero. And one of the nice properties of non-zero polynomials is cancellation. So a ring R has cancellation, that you can cancel stuff if whenever whenever xz equals yz and z is different from 0, then you can cancel the z and you get x equals y. So you might think that's always true. If you have xz equals yz, you can cancel the z. But that's not, it's not always true. Let's see if I can find a simple example. Suppose I take r to be the integers mod 12. So suppose I take x equal to 4 plus 12z, y equal to 8 plus 12z, z equal to 3 plus 12z. So xz is 4 plus 12z times 3 plus 12z is 12 plus 12z is 12z. And yz is 4 plus 12z, sorry, 8 plus 12z times 3 plus 12z, which is 24 plus 12z, which is 12z. So xz equals yz. Z is not 0, but x is not equal to y. So you cannot cancel in this ring. Xz equals yz, z is not 0, but it's not the case that x equals y. Right? So when can you have cancellation? Well, it turns out you have cancellation in a commutative ring if and only if the ring is an integral domain. So this is a lemma. Suppose we let R be a commutative ring. The lemma says R is an integral domain if and only if R has the property of cancellation. That is, xz equal yz and z different from 0 implies x equal y. So if the ring is an integral domain, it has the cancellation property. And if it has the cancellation property, then it's an integral domain. So that's what is the proof? Suppose R is an integral domain, which means no 0 divisors. So if xz equals yz, that means that xz minus yz equals 0. And we have distributive laws. That means that x minus y times z is 0. Z, R is an integral domain. No 0 divisors. So if x minus y times z is 0 and z is not 0, that means that x minus y has to equal 0 and x equals y, which means cancellation. It's cancellation. So if an R is an integral domain, then it has the cancellation property. Right? If R is an integral domain and xz equal yz for some z different from 0, then x minus y times z is 0, z is non-zero, x minus y has to be 0. So if an R is an integral domain, it has cancellation. Suppose R is not an integral domain. Then there exist x and z different from 0, and x times z equals 0. But also 0 times z equals 0. So that means xz equals 0z. But you cannot cancel, right? If you could cancel the z's, which are non-zero, you would have x equals 0, but x is not 0. So in an integral domain, there's cancellation, and in a ring that's not an integral domain, there's never cancellation. Yep. Woo. Well, we just did quite a bit, I think. In the notes that I posted on Blackboard last night, there's a chapter on ring theory, and I've just covered actually just about 4 pages of the notes, but there's a substantial amount there. Yeah. Let me look at another couple of examples. I mean, we already talked about matrices M2 of R. So the group of units of the 2 by 2 matrices with real numbers as coefficients, it's all matrices where the determinant is non-zero. This is usually called GL 2 of R. Here, M2 means 2 by 2 matrices. Here, GL stands for general linear. This is the general linear group. So this is a multiplicative group. Of 2 by 2 matrices. If we look at M2 of Z, this is all matrices A, B, C, D, where the coordinates are integers. And the multiplicative group would be all matrices where AD minus BC, well, only plus or minus 1, because you get the inverse by dividing by this determinant. But if the determinant isn't plus or minus 1 and it's non-zero, then you would get fractions here. You wouldn't get integers. So if you look at the matrices SL, this is with the matrices plus or minus 1, those are the invertible matrices. So if you have, for example, 3, 2, 4, 3, that's your matrix, I'll call it A. The determinant of A is 3 times 3 minus 4 times 2, which is 9 minus 8, or 1. And A inverse, you would be interchange these two and divide by 1. Change the sign of these. This would be the inverse. You can check that this times this is the identity. So these are all nice examples of rings. Matrix rings are very nice because they're non-abelian, non-commutative rings. They're nice to find. Ooh, okay. I think maybe that's more than enough for one lecture. Again, everything is written down legibly in the notes. We're going to have the second midterm exactly 3 weeks from today. Next week is spring break. We come back, and then there will be 2 classes that week. The following week on Monday will be a review, and the second midterm will be that Wednesday, May 4th. So I'll make sure I post it on Blackboard if it's not already there. And that's the story. Anyway, the ring theory notes are posted, and I really encourage you to spend as much time as you can trying to understand what's going on. And there'll be a homework assignment for after the break, but I'll put it up today, I think. It'll be problems that are at the end of section 1 of these notes. And so this will also be on the midterm because we need to learn about rings in this course. Okay. Any questions before we stop?
Professor, it might be too soon, but is there any way to post like a review sheet? So during like that free time next week, I might be able to just get ahead of it.
So the answer is yes, if tomorrow or Friday, you send me an email to remind me to do that.
No problem.
Okay?
Thank
And
you.
then I'll send it out. Thank you. It's a
Sure.
good idea. All right, all. Supposed to be a beautiful day, 70 degrees. So hope we all get to enjoy it. Also enjoy your break. Bye, all.
Thank you.